Hello, everyone, and welcome to Meet a Scientist, sponsored by New Mexico EPSCoR. I'm your host, Caitlin Everhart, over at Explora Science Center in Albuquerque, New Mexico. Today, we have T. David Burleigh, who's a professor and chair of Materials and Metallurgical Engineering at New Mexico Tech. Thanks for joining us today.
Yeah, you're welcome. Good to be here.
So why don't we start out with you just telling us a little bit about what it is that you do?
Okay, so I do a little bit of everything. So materials science it's a science of metals, polymers, ceramics, just understanding them all the way down to microscopic level, down to the atomic level. And so that's what we do is, so I do two things. I teach, and I have lectures at graduate level and undergraduate level. And then I have research programs going with students who are doing their research projects. My specialty is corrosion. So I work a lot in corrosion, trying to not corroding things, but I figure out how fast are they corroding, how to slow down their corrosion rate. And then the third thing I do is I do a little bit of consulting. Companies contact me and ask me about if I can solve these problems they have, and sometimes I can, and sometimes, most times I can. So that's what I do.
So for some of us who may not be familiar, what exactly is metallurgical engineering?
Okay, metallurgical is a science of metals. So as you can go all the way back to the Bronze Age, where you just heat up metal in a fire and hammer it, or you could move forward in which we actually start studying alloying. And the fact that they realized that, for example, steel, they realized that the thing between wrought iron and steel was just the amount of carbon. And they never realized that to the 1800s when they were actually a fellow dissolved steel and nitric acid and found this black powder left over, which he identified as carbon. So that's, just little things that try to make the science of what, how do you alloy metal, make it stronger, or how do you, and the crystal structure, and what is heat treating. You often see these blacksmithing videos where the blacksmith heats up it red hot and he quenches it in water or something. What's that doing on a microscopic scale? So that's what we try to understand, the theory all the way down to the atomic level of what makes a metal better. Then that way, once we have the science, we can go ahead and improve on it. We can make even better metals.
That's very cool. How did you get to where you are now? How did you end up in metallurgical engineering, of all things?
Funny question. So in high school, I had a really great physics professor, so I decided to major in physics. And so I went to Colorado School of Mines, majored in physics, but you have to have a minor. You need a minor. So I did a minor in metallurgy, and I got hooked on it. And it was a lot more fun to me than deriving equations. And so I kept on, went off to graduate school and did a master's welding titanium, master's thesis welding titanium. And then I came back and did a PhD in corrosion of glassy metals. So I just found the metals just really, really, really fascinating. So this is a funny thing. This is a heat sink. It's just a heat sink for aluminum. A bunch of electronics attaches to this, and then you can see here is that where the water flowed through. It's just kind of funny that where the water flowed through, as soon as it got turbulent, the water dissolved away the aluminum, and then it got laminar again. Then it turned this corner here and got turbulent. And so this is an example of erosion corrosion, which is kind of a funny problem to have. So that's one aspect of corrosion. And the whole thing was the pH of the water changed. So that was one of those. And then I've got some other demos. One of my hobbies is actually meteorites. Back when they were affordable. So that's just a little meteorite from Canyon Diablo. You can see it. But the thing is, if you look at the end of it, let's pull this one out here. If we zoom in on this thing right here, you can actually see there's lots of crystal structure. I'm going to zoom in on this one a little bit. Okay, and now you can see is that it's there's lots of different structure going on here, which is pretty fascinating. And so, and that comes from a very, very slow cooling rate. So understanding why the cooling rate is so. Let's see if I can get the autofocus to work a little bit better. Okay, so from the cooling rate, we can actually see these different structures inside this meteorite, and that's pretty fascinating by itself. But even more so is here's another one from another. This is from that's from Canyon Diablo. This is from Sweden. Here's a meteorite from Sweden. And we can see a totally different crystal structure here. Now these structures occur from cooling about 1 degree Celsius every million years. And so it's just a very fast. Sorry, let me get rid of that. So this is a very fascinating just the crystal structure. And you can actually see how the crystals keep changing. This is a gibbon from Africa. And so this is you can see the crystal structures on that one. We've actually heat treated it to bring out the different colors. You can almost see the colors there. And so you can see some of the patterns there. So anyway, it's fascinating to understand why these crystal patterns form, and we see them in the regular metal too. So and when I'm talking about crystal structure, let me just these are marbles, and so I glued them together to show this is called a hexagonal crystal, and then we can get different crystal structures. And so this right here would be a just simple cubic, and so. But the important thing is for steel, is that when you heat it up red hot, when it goes red hot, all the atoms move around and they form this cubic. It's called a face-centered cubic structure. And then when you cool it down, it goes back to this body-centered cubic structures, which is really pretty fascinating. So the atoms all move around as you cool and heat it, and then to get very brittle steel, what we have is yet a third crystal structure here, which I'll put out. So this is even and that's right here. This is called martensite, because our carbon gets stuck in between these spots right here, and they freeze it open. And so it kind of gives you an idea of what when we talk about crystal structures, what's going on. It's very, very quick, but it's some different.
Yeah, I can just imagine, going back in time, someone with a sword, and they have no idea what's going on at a molecular scale, why their sword keeps breaking.
Yeah.
It's so cool that this field can bring you into looking at medieval weaponry, looking at rocks from space, like
rocks. Yeah, exactly. Yeah. And the Romans all they heat treated their swords. They put their swords into charcoal. They heated them red hot for hours and hours. The slaves would pump the bellows, and they thought they were purifying their steel, but they weren't. They actually were diffusing carbon into their wrought iron to make it into steel. So, and then when they quenched it, they thought, well, there's lots of stories about the quenching, but I'll tell one gruesome story real quickly. But one king wanted one of his enemies killed a terrible death, so he ordered a red hot sword plunged through his body, which is horrible. But anyway, he did that, and then afterwards, the steel was much better quality than the other swords. And so they puzzled over it, and they put their best metallurgists onto the project, and they studied the problem. They said the man's spirit went into the sword, and so that's why it was stronger. So there's lots of old wives' tales too. So. And it took them a lot longer to realize it's actually just if you just could quench in water or oil and get a similar effect. Anyway, so there's lots of crazy stories, but the amazing thing is how metallurgy circled the entire world, from the Damascus steels to the samurai swords, and just the way of making steels and bronze swords and everything. So it's just historically, it's very fascinating. And then we try to transmit it forward and make better metals tomorrow.
Yeah, not quite working on swords in this day and age, but other things.
Yeah.
Well, is there any advice you would give to somebody who, thinks that this is all very interesting, but doesn't know how to get started studying it?
Okay, yeah. So first thing you got to do is you got to go to your classes. You got to go to school. Take all the math you can. You need math. Take all the chemistry you can. You need the chemistry. Take all the physics you can. You need all that background, and then just work hard and try to learn all you can. And the other fun thing is that my daughter calls material science. This is materials engineering also. She calls it the liberal arts major of the engineering world, because you can do almost anything. And you find people working on biomaterials. You find people working on ceramics and high strength polymers to make an elevator to the satellites. And so there's all sorts of things, but you have to have the background, and then just follow your curiosity and just keep going. And so study hard, don't skip school, go to your classes, and learn all you can about everything you can.
Thank you so much for joining us today. It's been a pleasure talking to you.
Okay, Caitlin, thank you for calling. Okay.